Artemis II is on the pad right now. SOS rolled out thereafter helium fixes, crew in quarantine, and will launch as early as April 1st. This 9 or 10-day lunar flyby will be humanity's return to the moon in over 50 years. But how does Orion efficiently escape Earth's gravity to reach that free return trajectory? It relies on a classical orbital mechanics hack known as the Oberth Effect, burning at maximum speed for way more energy gain per fuel drop. Let's break it down step by step and see why exactly how NASA uses it for this mission.
So simply put, the Oberth effect is the effect where the greater the velocity of a spacecraft relative to the planet, the greater the increase in kinetic energy, hence total energy, for a given amount of fuel, for a given amount of delta V. Now let's take an elliptical parking orbit. It's stable, and it has two very important points. A point which is furthest away from the Earth, and we call that the apogee, and the closest is the perigee. Now, in this stable orbit, the total kinetic energy and gravitational potential energy are constant. You add them up, and it's constant. Now, gravitational potential energy is based on the distance. The further you are from the center of the planet, the greater your gravitational potential energy. We're going to be a bit simple here. It's a little bit more complex than that. In kinetic energy, the faster that you are moving, the greater your kinetic energy. So at apogee, you're really far away. That means a high gravitational potential energy, hence a low kinetic. When you're at perigee, when you're closest, you have a high kinetic energy, but a low gravitational potential energy. So let's see if we can illustrate this. Now, for an impulse burn, and what we mean by an impulse burn is it's the force of the burn is the only significant factor increasing or decreasing the kinetic energy. So for the same amount of fuel, you'll have the same change in momentum, you'll have the same delta V, no matter what your initial velocity is. And that's quite important. Now, let's take a very simple example. We've got something at perigee, which is moving at 20 meters per second. Now, when it moves out to its apogee, it's at 10 meters per second. And we're going to give an impulse burn at both places of 10 meters per second. So, at perigee, it increases from 20 to 30 meters per second, and at apogee, from 10 to 20. And this rocket is very, very small. It's only 2 kilograms, and we'll explain why. Now, the kinetic energy is 1/2 mass times velocity. I've set the mass at 2 because 1/2 times 2 is 1, so therefore it's very easy to calculate the velocity, the kinetic energy. It's just the velocity squared. Now, let's look at change in kinetic energy. So at perigee, goes from 20 to 30, so that ends up being 30 squared minus 20 squared, which is 500 joules. Look at apogee. For the same delta V, we end up with only 300 joules. So at perigee, the impulse burn of the same delta V, the same amount of fuel, provides a far greater increase in kinetic energy, hence total energy. And that's the point. And it's that increase in total energy which converts into an increased apogee.
The Oberth Effect isn't magic. It's smart physics NASA exploits for Artemis II. With the launch possibly days away, this could be the most efficient escape burn in decades. Which orbital trick surprises you most? Comment below. If you like this, check my Apollo 8 versus Artemis II trajectory comparison for the full path. Hit like or subscribe for live updates post-launch.